All right, Ivan, are we ready to roll?
I think everyone's.
Oh, Ivan, I can't really hear you. Are we good to go?
I think everyone. Can you hear me?
I can't hear you. Can you hear me? You can send me a chat message. Great. Okay. So we'll get going then. So hello, good morning. Hope you're all doing well. Couple quick reminders. So there is a review session tonight from 5 to 6 for the chapter 2 quiz. That's tomorrow. So if you think that'll be helpful, definitely check it out. The link was in the last email I sent and also posted in Moodle. There's a recording from the Monday session already posted under Getting Started. So if you can't attend, feel free to watch the video. And so the review will cover the questions that are under the chapter 2 quiz heading. There's sort of review questions and solutions. So I recommend that you try those before you attend the review session, so you have a good sense of what you sort of need help with and what to pay particular attention to. So the chapter 2 quiz is tomorrow. Again, you'll need to find a 1-hour period to submit that. And so today we're going to be starting chapter 3, which is not on the chapter 2 quiz, but the Sunday mini quiz and homework will be on the section we talk about today. So just to sort of give you a bridge from chapter 2 to chapter 3, chapter 2 really is meant to help you understand the conceptual idea of the derivative. So the idea that, the instantaneous rate of change, also known as the derivative, will tell us how much a function is changing at a point, right? And the way we do that is by finding the slope of the tangent line. And we looked at doing that for individual points early in the chapter. And then later in the chapter, we said, okay, how do we talk about the derivative function, right? How do we graph it and talk about the entire derivative function? And so now that we've sort of learned and understand what the derivative is, what we want to do is figure out how we can streamline talking about the derivative function and finding instantaneous rates of change. And we do that through looking at and learning formulas for calculating derivatives. So there's going to be a pretty big shift from chapter 2 to 3 from sort of conceptual stuff to more formulaic stuff, which also means that there's a lot more algebra that's going to come in right now as we learn about the formulas and how to apply them. So I strongly encourage you, if you think you need help reviewing the algebra, to stop by Drop In Help and go over some of the stuff that we'll be doing so that the algebra doesn't become sort of a barrier to you doing the calculus, if that makes sense. And if algebra is fine for you, then you can completely ignore that. So that's just for people who maybe it's been a long time or you need a little extra help remembering stuff from algebra. We'll do a little bit of it today as we go along, but sort of overall, you want to make sure you have a pretty good understanding of algebra for this next 2 chapters. So I'm going to go ahead and switch over to the doc cam. Okay. So we're going to be talking mostly about formulas today, but I just want to highlight where these formulas are coming from. So the technical definition of derivative goes back to this idea that we started with slopes of secant lines with average rates of change, and we wanted them to get closer and closer to the point we were interested in until eventually they become one line, which was the tangent line. That's what we were doing. And so in the background, what was happening is we were finding the derivative function with this limit definition. And so if you apply this limit definition of derivative, which is what we were doing in practice, right? So that's what we were doing when we were computing these rates of change. You can apply this to a generic function, like a constant function or a linear function, and look at the results of what happens when you do these types of problems. And what you find is that when you look at similar types of problems like, mx, x squared, x cubed, when you apply this definition to a function, and you look at the derivative functions you get as a result, there's a pattern, okay? And it's that pattern that allows us to get formulas. And so we are lucky enough that somebody has done all this work so that we don't have to find those patterns. And we're going to be using these particular formulas, but just know that these formulas came from doing the same work we were doing in chapter 2, where we were approximating, with teeny tiny decimals, and then we looked for patterns, and then we were able to get formulas. So we are not going to be deriving formulas. That's the job of, people who study math at a much higher level. But they're taking the same types of things we were doing in chapter 2, and we use that to generate the formulas that we're going to be working with today. Okay, so that's the wrong page. Hold on 1 second. Okay. So what are these formulas and how do we use them? So today we're going to be working with a total of 5 formulas. We're going to start with 3 and we'll add on 2 near the end. And so the first 3 formulas that we're going to look at have to do with polynomials and power functions. And so we're going to be looking at things like x squared, x cubed, x to the 4th, or x to the half, things like that. So the x is in the base, and we have some power that's a number. So there's sort of 3 categories here. The first is that our function is a constant. Okay, so what does it look like when your function is a constant? Let me draw a picture. Okay, so we have some function that is, I don't know, f of x equals 4. So if your function is a constant, it's just a horizontal line, right? And if you think about the derivative at any given point, we know for linear functions, the derivative is the slope of the line, right? We learned that with cost functions and revenue functions. If it's linear, then the rate of change is the slope of the line. So for a constant function, that line is horizontal, which means that the slope of any tangent line is also horizontal, which is 0. So for any point on a constant function, the derivative will be 0 because the slope of that tangent line is 0. So that's our first formula. The next one says, okay, well, what if we have a line, but it's not horizontal, right? Okay, well, let's say we have something that looks like this, I don't know, 12x, right? It goes up from left to right. So we know that the change of a linear function is still just the slope. And so if we were to draw on tangent lines, they're going to have the same slope as the line. So all of these tangent lines are going to have a slope of 12 because that's the slope of the line. So that gives us our second formula. And our second formula says if you have m times x, so the slope times a linear term, the derivative everywhere, or the rate of change, is just the slope of that line, okay? And so we can see those pretty well visually, but then our third formula is not as well represented graphically, right? So we sort of have to trust the process and that this pattern is okay for us. So when you have x raised to some power, so that could be power 1, 2, 3, any sort of number, the derivative ends up being px to the p minus 1. So what does that mean, right? What does that look like in terms of a process? So that means if you have a function like f of x equals, I don't know, x to the 100, so any number, that we can find the derivative function and a formula for it by taking whatever that power is. It's going to come down to the front. So notice that p was in the power and now p is in the front. So we have 100x, and then we're going to subtract 1 from the original power. So since the power was 100 and we subtract 1, it becomes 99. So in summary, if we have a constant, the derivative is 0. So constants are terms that are just numbers by themselves and not attached to any function. If we have a linear term, right, m times x, where m is any number, the derivative is just that m, because that's the slope of the line. If we have x raised to any other number, then our formula is that that number comes down out front and we subtract 1 from the power. So what we're going to be doing is we're going to be practicing these formulas in a lot of ways. and adding in other general properties of derivatives to continue practicing these formulas. So we're going to go ahead and start with this set of functions, a through g, and we're going to practice taking derivatives. So I'm just going to read them to you real quickly in case you can't see them if you're way in the back and it's small. So for a, we have f of x equals 7. Then we have f of x equals 10x. Then we have f of x equals x squared. Then we have f of x equals x to the 5th. Then we have f of x equals x to the negative 4. Then we have f of x equals x to the 2/3. And then the last one is f of x equals x to the negative 1/5. So you definitely have to do a little bit of algebra in the later ones when you are subtracting one from the power. So be really careful about that with negative numbers and fractions. But I'd like you to take 2 minutes and try out these examples and see if you can figure out which of these 3 formulas to apply and then what the derivative function will look like. Okay, so try that out and then we will go through it together. Okay, take about 30 more seconds. Okay, so let's go term by term and see if we can figure out which rule to use and then how to apply it. So starting with our first function, we have f of x equals 7. And so notice that the 7 here is not attached to any variable, which means it's a constant all by itself. So that means we're going to use our first rule here, where if your function is a constant, that the derivative is going to be 0. So everywhere on this function, the derivative equals 0. The next one, we have 10x. So notice that 10x is a number times x. This is a linear term, which means we are now looking at the second formula, mx. And so when we take the derivative is just the slope of the line because it's a linear term, and the slope there was 10. So finally, for the next 1, 2, 3, 4, 5, all of these are in the form x to the p, where we have x in the base and it's raised to some power p. So we're going to be using the power rule for all the rest of these. Okay, so let's see what shakes out here. So we start with x squared. The power rule says that the 2 comes down out front and we subtract 1 from the power. So we get 2x to the 1. We don't usually write the 1, so we would write this as 2x. Okay. The next one, we have x to the 5th. And so here, when we take the derivative, the 5 is going to come down out front, and we subtract 1 from the power. So we have 5x to the 4th. So again, we're employing this power rule where the power comes down in front, and then we subtract 1 from the power. For the next one, we notice that we have a negative power. So that means we have to be really careful when we subtract 1 in our last step here. So for x to the negative 4, the negative 4 comes down out front, the negative comes with it, the whole entire thing. And then we subtract 1 from the power. So negative 4 minus 1 is going to be negative 1. Okay. So hopefully you're able to figure that one out. And then for f, we have x to the 2/3. So here the entire power comes down out front. So we have 2/3 x, and then we subtract 1. 2/3 minus 1 is going to give us negative 1/3. Okay, so again, be really careful with fractions. If it's been a while since you've done them, you know, you need to be extra careful when you set them up, but we'll do the fraction on the together. So the last one, we have x to the negative 4/5. So the negative 4/5 comes down out front, and we're going to subtract 1 from the power. So just as a reminder, if we have negative 4/5 minus 1, that's the same thing as negative 4/5 minus 5/5. So we want to come up with a way to represent 1 with a common denominator. So negative 4 minus 5, that's going to give me negative 9/5. Okay, so that's how we're sort of setting up and dealing with subtracting 1 from fractions. Okay, so this is sort of a first step using these particular rules. Now, there's some properties that are going to apply to all the derivative rules that we're going to start to learn about. And the first one is called the constant multiple rule. So the constant multiple rule wants to answer the question, what happens if you take the derivative of a function that has a constant multiplied in front? Okay, so what's an example of that? So let's say we had 10x to the 9th. Okay, so this is why we need a constant multiple rule. We need to figure out how does the 10 come in when our function is x to the 9th? Can we still do the same things? Does anything change? And what we find out is that that constant can actually be pulled out front, and we can take the derivative of the function, just like we did before, and we end up with constant times f prime of x. So what does that mean? That means when we take the derivative, the constant, which was 10, that's multiplying a function, multiplies the derivative of that function. So we take the x to the 9th and we apply the power rule. So we get 9x to the 8th. So our derivative then, we can multiply the two constants together and we get 90x to the 8th. So the way that this happens in practice is that we say the 9 comes down and it multiplies the 10. That's where we get the 90, and we subtract 1 from the power. That's the 8th. So what's happening in the background is what's called this constant multiple rule. And one of the important distinctions here is that this is different than the constant derivative rule. The constant derivative rule says that if your function is just a constant, the derivative is 0. The constant multiple rule considers what happens when your constant multiplies a function. Okay, so that means we have a constant in front of and attached to a function. It's not by itself, because if the 10 was just by itself, if it was just f of x equals 10, we would just be using that constant rule. Okay, so we're going to practice with some constants in front of our functions here. So we have another set to try. Again, the goal is to really practice rules as much as possible to get really comfortable with them. So really quickly, I'm just going to read through the functions in case you can't see them, and then I will go ahead and let you try to find the derivatives. So first we have pi. So pi is 3.14, on and on. Then we have 4x cubed, then 9x to the 20th, then negative 3x to the fifth, 6x to the negative sixth, then 6x to the 1/3, and finally the last one is 7x to the negative 2/5. Okay, so again, you're going to be pairing this idea of the constant multiple rule for the things like 4 and 9 with the rule up here on how we do the derivative. So I want you to take 2 minutes, see how many of these you can do. You don't have to do them in order. You can sort of do the ones you want and feel most comfortable with, and then try some of the harder ones, or you can start with the harder ones, either way, but try them out and then we'll go through them together. Okay, take about 30 more seconds. Okay, so for the first one here, we just have pi. And so what we notice is that the constant is by itself. Okay, it's not attached to a function. There's no x there, which means that we're just using the constant derivative rule here. And this one is 0. So that one was a little tricky. Hopefully you caught that, but if not, hopefully you'll remember that for next time. For the rest of them, however, we do see functions, right? We see x's in there. And so we're going to be using our power rule paired with our constant multiple rule. So the next one here, we have 4x cubed. So when we take the derivative, the 3 comes down to multiply the 4. That gives you 12. And then we subtract 1 from the power. So we get 12x squared. For the next one, we have 9x to the 20th. So when we take the derivative here, we're getting a pretty big number. We have 20 times 9. So 180x. And now we subtract 1 from the power. So that's to the 19th power. For the next one, I want you to notice that there's a negative 3 in front. So when we take the derivative, that negative has to stay. So negative 3 times 5, we get negative 15x, and we subtract 1 from the power. So negative 15x to the 4th. For part E, we have 6x to the negative 6. So again, we're aware of this negative because when the negative 6 comes out, that's going to multiply the positive 6. So we get negative 36x, and we subtract 1 from the power. So that's to the negative 7th. And then over here, the next one, we have 6x to the 1/3. So again, we're being really careful with fractions. The 1/3 is going to come out and multiply the 6. So 6 times 1/3 is 2x. And now 1/3 minus 1 is negative 2/3. So then finally, the last one, we have 7x to the negative 2/5. So the negative 2/5 is going to come out. and it's going to multiply our 7 here. So we're going to get negative 14 fifths. So remember, if you have a constant and you are multiplying by a fraction, that constant multiplies into the numerator. And then we subtract 1 from the power. So negative 2 fifths minus 1 is the same thing as negative 2 fifths minus 5 fifths, which is going to give us negative 7 fifths. Okay, so as you think about this constant multiple rule, the idea is really that it gets incorporated when that power comes down. So just try to be sort of extra careful about that. I will mention that the common mistakes that students make when they're doing derivatives tend to be either the algebra. So it's not the process of bringing the power down, it's the process of subtracting 1. Or they forget about the power altogether. So they bring the power down, and they forget that they have a new power, which is 1 less than the old power. And so they just bring it down, but then leave it as X instead of considering what the new power will be. So the more we practice this, the better we get overall. Now, there's a couple of other algebra, I don't know what they're called, algebra strategies that we need to use. Because of the way we often see our problems. So the next problem is meant to help you try to remember and think about how we rewrite functions algebraically. So here we have the square root of x, right? And then we have 4 over x cubed. And then we have the 5th root of x squared. And so for all 3 of these functions, they need to be rewritten first algebraically into a form that is x to the p, so x raised to some number. And so what I want you to do is think about if you can remember how we might turn these symbols, like the root symbol, the 5th root symbol, into powers, or how we get this term out of the denominator, because we can't take the derivative while it's in the denominator. So we want to think about how we can rewrite these and then apply the derivative rule and find the derivative. So if you don't remember any of these, try your best guess. If you do remember some of them, go ahead and do it. Take about 2 minutes, and then we'll go through it together and carefully review these algebra rules that are going to become really important. Okay, take about 30 more seconds. All right. So again, the purpose of this problem is really to help you remember from algebra how we rewrite different types of algebraic terms. So what we're going to do is we're going to go through and we're going to first talk about how we rewrite each of these, and then we'll go back through and do their derivatives. So when you have the square root of x, that is the same thing as taking the 1/2 power of x. So this symbol, the square root symbol, is a mathematical representation of the 1/2 power. So we would rewrite that as x to the 1/2. For the second one, 4 over x cubed, we have an algebraic rule that if there's a term in the denominator and you want to bring it up to the numerator, you can change the sign of the power. So that means here we had x cubed to the positive 3. If we want to get it out of the denominator, we'd bring it up and write it as 4x to the negative 3. Okay, so by changing the sign of the power, we can move things to the denominator. And then finally, we have a fifth root here and an x squared term. So this is going to be 2 steps, but similar to A. So the first step is to get rid of the symbol and turn it into a number. So instead of the fifth root of x squared, we have x squared to the 1/5 power. So if you have a fifth root, it's 1/5. If you have a third root, it's 1/3. If you have a square root, it's 1/2, so on and so forth. But we have a power now raised to a power, and our formula is x to a single number. So if you have a power raised to a power, you can multiply those 2 numbers together. So this can be simplified into x to the 2/5. Now, again, I really want to make sure that we're clear that I didn't do any derivatives here. All I did was some algebra to rewrite the function into the right form. I still have to apply the power rule formula from before to find the derivative. So now I'm going to go through and we'll do that for each of these. So we start with x to the 1/2. So here the 1/2 power comes down and we subtract 1 from the power. So 1/2 minus 1 is -1/2. Okay. Now for the second one, we have 4x to the -3. So when we take the derivative, the -3 comes down to multiply the 4, giving me -12x. And then we subtract 1 from the power, which is -12x to the -4. And then for the last one, we have x to the 2/5. And so the derivative will be 2/5 x. Now we subtract 1 from the power, so to the -3/5. Okay, so in chapter 3 and chapter 4, these are common things that we do all the time to rewrite functions. So if that's something you haven't done in a long time and don't remember very well, I strongly encourage you to go to Drop In Help and just ask for some practice problems on rewriting algebraic functions. We can give you a ton to practice so you get used to this. But one thing I want to make sure you know is that you don't forget that that is just a simplification step. Sometimes students will rewrite the problem and say that that's the answer because they forget to actually do the step where they take the derivative. So this is just rewriting, but then we need to apply the formula. Okay, so what else do we need to think about? Well, so far, everything we've sort of looked at has been a single term, right? So 4x cubed, single term. So we have the question, what if we have more than one term? And this can happen in a couple of ways. So today we're going to be talking about sums and differences. So that means if you have terms that are separated by addition or subtraction, what changes in terms of taking the derivative, if anything, right? And the answer is, it doesn't really. We're going to take the derivative of each piece individually and put them back together using the same sign that was there. So, you had f of x plus g of x, then the derivative is f prime of x plus g prime of x. If you had f of x minus g of x, that's f prime of x minus g of x. So with addition and subtraction, we can just go term by term and apply our formula. I will tell you that you cannot do this with multiplication and division, and we're going to have to learn some special formulas on how to deal with that, but that will be later next week. So we're going to go ahead and practice this. So this is going to pull in addition and subtraction just to apply this rule, but then also you'll see there's some square roots here, there's some terms in the bottom so that we can keep practicing these algebraic rewrites as we go. Right? And so I'm just going to quickly read these to you in case you can't see them, and then you're going to go ahead and find the derivative. So the first one, we have x to the 5th minus 2x squared plus 6x plus 1. For part B, we have 3x cubed minus x to the 1/3 plus the square root of x. For C, we have 10x to the 4th minus the 4th root of x plus 2 over x cubed. And then for part D, we have negative 3x to the negative 3/4 plus 2 square roots of x. Okay, so I want you to take 2.5 minutes and write out what the derivative function is going to look like for these. And again, you're going to apply the rules term by term. And remember, we have 3 rules, so try to figure out which one is the most appropriate for each term. Okay, so try it out, and then we'll go through it together. And like I said, about 2.5 minutes. Okay, take about 30 more seconds. All right. So again, when we see a function that has terms separated by addition or subtraction, we want to apply our formulas term by term. So for this first one, we start with our first term, which is x to the 5th. We apply the power rule. So the 5 comes down, subtract 1 from the power. And we have 5x to the 4th. For our next term, we're going to be using the constant multiple rule with the power rule. So the 2 comes down, multiplies the 2 in front. We get 4x to the first power. Again, we don't usually write the first power. You can. It's not wrong if you do. But conventionally, we don't write the 1 power. The next term, we have 6x. So this is a linear term. So this goes to our formula. It says if you take the derivative of a linear term, you just get the slope of the line. And then finally, the 1 is by itself. So that's the constant derivative rule. And so the derivative of 1 will be 0. So our first derivative looks like this, 5x to the 4th minus 4x plus 6. Okay, so let's look at the next one. So for the second one, what I want to point out is we do have a square root of x term. So we do need to think about how we would rewrite that. So remember that the square root of x is the same thing as x to the 1/2. So when we deal with that term, we want to think about it as x to the 1/2. So for f prime of x, the first term, we have 3x cubed. The 3 comes down to multiply the 3, giving us a 9. Subtract 1 from the power. We have 9x squared. For the second term, we have x to the 1/3. So the 1/3 comes down. Subtract 1 from the power. So we get minus 1/3 x to the negative 2/3. Sorry, my 3 looks a little goofy here. And then for the last term, this is where we have to remember that the square root of x is the same thing as x to the 1/2. And so when we take the derivative, we're using the power rule. The 1/2 comes down and we subtract 1 from the power. So we end up with something that looks like that. For the third one here, there's 2 different rewrites that we need to do. So the 4th root of x is the same thing as x to the 1/4. That's one thing we'll have to consider. And then 2 over x cubed is the same thing as 2x to the negative 3. So both those terms need to be reconsidered before we can apply the power rule. So here we have 10x to the 4th. We take the derivative using the constant multiple rule. So when the 4 comes down, it multiplies the 10. So I get 40x, and then I subtract 1 from the power. So 40x cubed. Now for the second term, I notice that that is the 4th root of x. So that's when I'm considering x to the 1/4 here. So when I take the derivative of x to the 1/4, I get 1/4 x to the negative 3/4. Okay, so again, the 1/4 comes down, and then I subtract 1 from the power. And then for the last term, I notice that this is a plus, but I also notice that a negative 3 is going to be coming out. So I'm going to wait and not write plus, because instead I'm going to look at what happens with the derivative. So the negative 3 is going to come out and multiply the 2, which gives me minus 6x to the negative 4. Now you can certainly write that as plus negative 6. That is the same thing. It's just a matter of preference. Okay. Now for the last one here, what do we got going on? So again, I see a square root, but we've already talked about the square root up here. So I'll just keep that in mind when I do that term. Okay, so the first term here, I have a negative 3, and I'm multiplying it by a negative 3/4. So the negatives are going to cancel, and I'm going to get 9/4 x. Now negative 3/4 minus 1 is negative 7/4. Okay, and then plus, so 2 square roots of x is 2x to the 1/2. So when the 1/2 comes down, it's going to multiply that 2, and 1/2 times 2 is going to give me a 1x. And then 1/2 minus 1 is going to give me negative 1/2. Okay, so again, we're trying to practice all these rules, but also sort of reviewing the algebra as we go in things like subtracting 1 from the power and rewriting things. Okay, so our derivatives look like this. And again, the main point for this set of problems here is that if things are separated by addition and subtraction, you can just treat them term by term. Okay, so what do we add on next? The second derivative. So as a reminder, the notation to indicate that we're taking a second derivative, there's 2 hash marks, or you might see something like this. These are the 2 notations that indicate that you are going to be finding a second derivative. And how do we compute second derivatives? So first, find f prime of x. So you're going to find the first derivative using the rules we've been talking about. Then apply the same rules to f prime of x to get f double prime of x. So what does that mean? So you start by finding your first derivative, And then once you have your first derivative, you look at each of those terms and say, which rule do I need to use? Is it the power rule? Is it the constant rule? And you apply the appropriate rules to the first derivative terms to get the second derivative. So it's the same rules, just applied now to the first derivative to get to the second derivative. But you do have to find the first derivative first, if you start with f of x, to then be able to apply those rules to get to the second derivative. So let's try an example of this. So we have 6 minus 3 over x plus 3 over x squared plus x to the 1/3. And then the second one, we have x to the e. So think about what e is. E is just a number. How might we think about writing that? And then the last one, we have 6x to the 7th minus 20 square roots of x. So again, we're still just practicing some of our algebra rewrites. We're practicing first derivatives and recognizing different things. So for each of these, I want you to find both the first and second derivative. So what I would recommend is going through and finding the first derivative for all three functions, so you can practice that, and then going ahead and finding the second derivative for each function if time allows. So I will give you 3 minutes, try to work those out, see how far you can get, and then we'll go through it together. Okay, take about 30 more seconds. All right. So for part A, I noticed that 2 of the terms need to be rewritten. So 3 over x is going to become 3x to the negative 1. So we can bring up the x by making that 1 power negative. 3 over x squared is going to become 3x to the negative 2 so that we can apply the power rule. So now that we've thought about how we will rewrite these terms, we can go ahead and find the first derivative of this function. So here, the derivative of 6 is going to be 0. So I actually can start with this term here. So I have minus 3 over x. So minus 3x to the negative 1. When the negative 1 comes down, it's going to cancel out this minus right here. And so that's just going to leave me with 3x to the negative 2. And now for the next term, I have plus 3x to the negative 2. So when I take the derivative of that, the negative 2 is going to come down to multiply the 3, giving me negative 6x to the negative 3. And then finally, the last term, I have x to the 1/3. So I have plus 1/3 x. Now I subtract 1 from the power. 1/3 minus 1 gives me negative 2/3. Okay. So fortunately, if you have to rewrite things for the first derivative, you tend to not have to write them for the second derivative because they're already in a form that you can work with. So to talk about the second derivative here, we're again going to go term by term to see which rules we're going to apply. So for the first term, I see a power rule here. So the negative 2 is going to come down to multiply the 3. So negative 6x, subtract 1 from the power. So negative 6x to the negative 3. For the next term, the negative 3 will come down to multiply the negative 6. That gives me positive 18x, and I subtract 1 from the power. So 18x to the negative 4. And then for the last term, negative 2/3 is going to multiply positive 1/3, which gives me minus 2/9 x to the negative 5/3. Okay, so again, you have to go through the first derivative to get the second derivative, but as long as you're careful as you go, you know, it's not too terrible. You just have to be really careful with negatives and fractions and things like that. So let's take a look at the next one. So here we have x to the e, right? E is kind of a weird, goofy thing to think about because e is a number represented in nature, right? It's a lot like pi, but it's got a different value. It's about 2.71. It comes up a lot in modeling things based in biology. So if we have x to the e, we still have a power rule because e is a number, okay? It's just an irrational number. So when we find the first derivative, the power comes down in front, so the e comes down, and then we subtract 1 from the power. So we can write that as e minus 1, right? We're not going to try to combine that into a decimal because this is an irrational number. So it's more accurate, it's exact to leave it as e minus 1. Now, when thinking about the second derivative, we have this e from the first derivative, but then e minus 1 comes down and multiplies the e. And then we subtract another 1 from the power. So we end up with something like this, where we have e times e minus 1, and now our power is x to the e minus 2. So this is a little tricky, but it's a really good way to illustrate how we deal with irrational numbers and how we might write things and think about them, okay? So that's how we would think about B. And then for part C, the first term, we have 6x to the 7th. So we can do a power rule here with a constant multiple rule. The 7 comes down to multiply the 6. And I get 42x to the 6th. Now, the second term, I see the square root of x. As a reminder, the square root of x is the same thing as x to the 1/2. So if I have minus 20x to the 1/2, when the 1/2 comes down in front, it will multiply the 20. So minus 10x, and now we subtract 1 from the power. So we get minus 10x to the negative 1/2. So now when we go to do the second derivative, we again are going to go term by term. So we have 42 times 6, which is 252x. We subtract 1 from the power, so x to the 5th. And then for our second term, I notice that I have a minus and that I have a negative half coming down. So the minus is going to cancel, and I'm going to get plus 5x. Half of 10 is 5. And then negative half minus 1 is to the negative 3/2. Okay, so that's what the second derivative looks like there. So when you're dealing and trying to figure out second derivatives, things like that, just remember you go through the first derivative and then we're using the same strategies that we were before. Okay. I'm going to skip ahead for a minute. There's a couple of examples I want to make sure that we do. If we have time, we'll go back. If we don't, you can watch example 6 on the videos. But I want to make sure we talk about the equation of the tangent line. This is going to be a pretty important example for us, as you'll see that we end up doing this type of problem throughout the entire chapter and into chapter 4. So as a reminder, we talked a lot about the tangent line when we were in chapter 2, because the derivative, or the instantaneous rate of change, gives us the slope of the tangent line, right? So now what we want to do is we want to take that idea, okay, well, if we know something about the slope of the tangent line, are we able to get the equation of the tangent line, like the entire equation for that line? And so as a reminder, when we talk about the equation of a line, right, we're talking about y equals mx plus b. So we want something in that form, right? So how can we use what we know about derivatives to find the equation of the tangent line to the function x squared minus 4x plus 1 at x equals 3? Okay, so what we want to do in order to find the equation of a line, you either need 2 points on a line or 1 point of the line and the slope of the line. And we know from before that we can get something about the slope. So let's start by thinking about that. We know that the derivative gives us the slope of the tangent line. We also know how to find the derivative function based on the things we've been doing today. So if we were to find the derivative of this function, we would go term by term. So the derivative of x squared is 2x. The derivative of 4x, this is a linear term, is 4. And the derivative of 1 is 0 because that is a constant. So this is the derivative function, which means that it will give me the rate of change at any point that I want, okay? But the point that I want is x equals 3. So I plug that point into my derivative, and I get 2 times 3 minus 4, which gives me 2. So when I plug a value into the derivative, that gives me the slope of the tangent line at that point, which represents the rate of change. And so since this is the slope of the tangent line, tangent line at x equals 3, that means that when I'm thinking about the equation of my tangent line, that the 2 is the m, right, in the equation of the tangent line. So by finding the derivative and plugging in the value, that gives me the m, the slope of the tangent line. Now, as I mentioned, if you have the slope of a line, you also just need a point on that line. So how do we figure out a point on the line? Well, what I want you to remember is that when we were doing derivatives, we were talking about the tangent line touching the function we were interested in at 1 point, right? So we had some function and the tangent line touched at 1 point. And so what we can do is we can find that 1 point that is shared between the function and the tangent line. And we can do that by taking the value of 3 and plugging it into the original function, because that's going to give us the corresponding y value. And it's also going to tell us where the tangent line touches. So if we take 3 and you plug it into the original function, you get 3 squared, which is 9, minus 4 times 3, so minus 12, right? So now we're at negative 3, plus 1 gives me negative 2, okay? So f of 3 is negative 2, and so that tells me that the point that is shared between the tangent line and the function is the point 3 comma negative 2. So how do I use that now to find the equation of my line? Well, I start by plugging in my slope. I know that that's 2. And I get y equals 2x plus b. If I now plug in my point, 3 comma negative 2, I plug in the 3 for x and a negative 2 for y. And that allows me to solve for b. Okay, so 3 times 2 is 6. I subtract the 6 over to the other side, and I get b equals negative 8. So now I have the slope and I have the b, so I can put it all together to get the equation of my line, which is y equals 2x minus 8. Okay, so again, the 2x, the 2 came from the slope, and the negative 8 came from the equation of the line using the shared point. So what's going to end up happening in this class is we are going to be doing find the equation of the tangent line through all sorts of examples, and what's going to change is the function. As we learn different techniques of finding derivatives, we'll have different functions, but we're going to be doing the same problem again and again. And so we'll actually do another practice problem of this in just 2 or 3 minutes. But this is sort of the map of how we find it. We find the derivative, we plug in the x value or t value and get the slope of the tangent line. Then we plug the value into the original function to get the shared point. Then we use the slope and the shared point to construct the equation of the tangent line. Okay, so as I mentioned, we are going to do 5 formulas today, and we focused on the first 3. So I want to bring in the last 2 formulas that we're going to introduce today, which is sine and cosine. So again, these formulas come from mathematicians looking at patterns of what happens when you take derivatives at every single point. And it turns out that when you take the derivative of sine at every single point and you graph it, you get cosine, right? That's convenient. And when you take the derivative of cosine, you get negative sine. Okay, so we have to be a little bit careful about remembering where that negative is, but otherwise they are just reciprocating back and forth. Sine goes to cosine, cosine to negative sine. So we add these 2 formulas to our list. Okay, so we have sine goes to cosine and cosine goes to negative sine. As we add formulas to this list, the other properties of derivatives also apply. So if you have things separated by addition and subtraction, and there's sines and cosines, we can still go term by term. Constant multiple rule still applies. Second derivative rules still apply. So what we're going to do is we're going to do some practice problems with sine and cosine, just to make sure we remember how to apply those things we were talking about with just a couple new formulas. So we're going to start with this particular one here. Right, so for each of the following functions, I want you to try to compute the first derivative and the second derivative of each of the functions, right? And you'll see that each one has at least part of it that is brought in sine or cosine. So I'm going to give you about 3 minutes to try this out just to get comfortable with sine and cosine, and then we'll go through it together. Okay, take about 30 more seconds. All right. So for the first one, we have 6 cosine x. And so here we're using the constant multiple rule. So that 6 is going to multiply the derivative of cosine. The derivative of cosine is negative sine. And so we have 6 times negative sine x. And the convention in math is if you have a negative, it sort of gets pulled to the front of the term. So we would write this as negative 6 sine x. Okay. Now for the second derivative here, we still have the constant multiple rule, where now the constant is negative 6. And the derivative of sine x is cosine x. So we get negative 6 cosine x. So you see we get something similar to what we started with, which is pretty expected since we're varying back and forth between sines and cosines, and what's changing is whether they're negative or positive. Okay. So for the second one, we have sine of x plus 1. The first derivative here, the derivative of sine, is cosine x, and the derivative of 1 will be 0 because that's a constant that's by itself. And so then the second derivative is going to be the derivative of cosine, which if we go to our chart, is negative sine. Okay. And then for the third and final, the first derivative, we have 2 terms, right? And they're separated by subtraction, so we can go term by term. We have x cubed, the derivative of x cubed is 3x squared, minus 2, now the derivative of sine is cosine. So I have 3x squared minus 2 cosine x. Now for the second derivative, we start with the first term, the derivative of 3x squared is 6x. And now here, I know that cosine is going to turn into negative sine. And so I'm looking at this minus, and I'm just being careful, but I'm going to cancel out the minus with the negative. And so plus 2 sine x. And again, cosine turned into negative sine, but since this was a minus, that canceled. So that's what the first and second derivatives look like when thinking about terms that might have sine and cosine in them. Okay, what I want to do now is have you try equation of the tangent line, right? We went through one together, but now this is one that's going to use cosine here. So think about the process in the one we did and how we might apply the same process here, but now our function is slightly different. Okay, so we're trying to find the equation of the tangent line to f of x equals 3 cosine x at x equals pi over 2. And I will caution you that if you don't remember the unit circle and what the values are when you're plugging in pi over 2 and you're using your calculator, please make sure that it's in radians, okay? Because every measurement we're doing is in radians. And if yours is in degrees, all of your answers are going to get all goofy and not be correct. So make sure that if you're relying on your calculator, that it is in radians, okay? So take about 2 minutes, see what you can work out, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so again, for equation of the tangent line, we need a point and slope. It doesn't matter which one you compute first, but let's go ahead and do the slope. So to find the slope of the tangent line, we need to first go through the first derivative function. So the derivative of 3 cosine x, remember the derivative of cosine is negative sine, so we're going to get negative 3 sine x as our general function. But then we need to plug in the value that we're interested in evaluating. So here, we're looking at what's happening at pi over 2. So we have negative 3 sine of pi over 2. So sine of pi over 2 is 1. So negative 3 times 1 gives us a slope of negative 3. So our slope is negative 3. And then to get our point, we need to plug in the value we're interested in into the original function. So f of pi over 2, we have 3 cosine pi over 2. When we plug that into the original, cosine of pi over 2 is going to be 0. So we have 3 times 0, which is 0, which means that our point is pi over 2, comma 0. So now we need to put that all together. Okay. So we start with our slope. So we have y equals negative 3x plus b. Then we're going to bring in our point. So y is going to be 0, and x is going to be pi over 2 plus b. I do want to give you another word of caution here. You do want to leave this as pi. If you turn it into a decimal, it's no longer accurate. It becomes an approximation. So we want to leave things in terms of pi so that they are exact. So to solve for b, I take negative 3 pi over 2 and I add it to the other side. So b equals positive 3 pi over 2. So putting everything together now with my slope and my point, my b, I get y equals negative 3x plus 3 pi over 2. Okay, it's not uncommon to have pi's in your answer when you're dealing with sines and cosines, because that's sort of the common values that we're looking at. So again, when we're looking for the equation of the tangent line, we're looking for the slope, we're looking for the point, we put it together and we get the equation of the tangent line that touches this function, 3 cosine x, at the point x, or at the point x equals pi over 2. Okay, so try those out. If you want to see the example that we skipped before, example 6 or example 11, which we didn't get to, feel free to watch that on the video. It's just a couple of extra examples of plugging things in, but hopefully you have a good sense of these derivative formulas. So we will pick up with this on Tuesday. So have a good weekend and don't forget to take your chapter 2 quiz tomorrow.